Now that we've discussed the theory of operation and the four strokes of a small gas engine, we're going to move and start discussing each system independently. Remembering that these systems are working simultaneously, but for sake of clarity, we're going to talk about each one individually, as well as common issues we may encounter that's going to require us to troubleshoot our engines. Let's begin with a quick review of the four strokes of a small gas engine. We'll begin with the intake stroke. Remember, this is where the piston is moving down the cylinder bore, creating a void or a vacuum in the cylinder, allowing atmospheric air to pass through the carburetor, collecting atomized fuel as it moves into that vacuum. Once the piston reaches top or bottom dead center rather, it begins to move back up in the compression stroke, and it compresses the air fuel mix to its optimal ignitability when it's at top dead center. At that moment, the spark plug ignites that air fuel mix, and we begin the power stroke where the piston is forced down the cylinder bore and rotating the crankshaft. As that rotation gets to the end and then we reach bottom dead center again, the piston begins to move back up in the exhaust stroke to get rid of all exhaust fumes and waste gases. Again, it's important to remember that these four strokes are completed with 2 revolutions of the crankshaft. So our objectives for this module are going to begin by describing the purpose of the fuel system, as well as the main components of all fuel systems. We'll also identify the types of fuel systems we find in small gas engine applications. And then we'll move into talking about carburetors as a component of this fuel systems, and describing components common to all carburetors. And then we'll talk about some common problems we see associated with fuel systems, as well as how to troubleshoot those issues. So if we look at the fuel system itself, and we very much oversimplify it, all fuel systems are basically comprised of 3 components: some sort of storage tank, a carburetor, and the engine itself. And so our 3 main functions of the fuel system then are to store fuel, deliver the fuel to the combustion chamber, and in between, change the liquid gasoline into vapor. Because, believe it or not, liquid gasoline does not burn. It must be vaporized before it's combustible. And that is the job of the carburetor. So let's look at the components of a fuel system in a little more detail. So most fuel systems can be comprised of at least a fuel supply, which is going to be our fuel tank. Our fuel lines are going to deliver the fuel where it needs to go. A fuel pump, should there be a situation where the tank may be low to the ground and a gravity-fed situation might not work. You may also have a fuel filter somewhere in between here. And then the carburetor itself, that's going to be the final place where the fuel will be atomized and delivered to the combustion chamber. So now we'll talk a little bit about the common types of fuel systems. Those are going to be a gravity fuel system, a suction fuel system, a fuel pump system, and a pressurized fuel system. One of the most common in a small gas engine application is going to be a gravity fuel system, especially in areas that are things that are pretty small, maybe our walk-behind mowers, generators, pressure washer, snow blowers, those types of things are relatively small piece of equipment. Small application is going to use a gravity fuel system where the fuel tank is located somewhat above the carburetor, and simple gravity is used to deliver fuel from the tank to the carburetor. A suction fuel system is going to be a little less common in the small applications. This is going to use the movement of the piston and valves to actually utilize the vacuum created by the piston to help pull fuel into the combustion chamber. Another common occurrence of systems is the fuel pump system. This will be on a little bit larger applications such as riding mowers, zero turns, where a mechanical pump is going to be used to force fuel from the tank to the carburetor. And then the final system is the pressurized system that's going to use some sort of compression within the tank to force the fuel out of the tank to the carburetor. In a moment, we'll see a video from Briggs and Stratton that's going to discuss this in more detail, but it's important to talk about the fact that carburetors come in a lot of shapes and designs and sizes, but they all do the same thing regardless of how they look. Now, obviously, depending on how they're shaped, they may not be universally fit to all engines, but they all do a few of the same things or have some of the same components that we'll see. They all have to have some sort of fuel supply. In this case, we have our fuel bowl, where we actually will have fuel delivered directly to the carburetor bowl, and that little bit of gasoline will be what's vaporized up into the carburetor. Some older walk-behind motors especially had what we called a tank-mounted carburetor, and so this carburetor here will be oriented with this piece, this jet, and we'll get into what that means in a minute, is actually located in the tank, so we don't have a bowl per se like we do with the other two examples on this slide. We're using the entire gas tank as its own bowl. But either way, the same principles are going to arise. We have the same components as far as a throttle side, a choke side. We'll get into what the venturi means, but that'll be in there. So regardless of the specific shape or orientation of the carburetor, they're going to do the same job. And because of that, we can ultimately start to understand how they work, and even more importantly, diagnose potential issues or problems we have associated with carburetor. Now that we have looked at the fuel system kind of over big picture and saw that we have various different configurations of carburetor, let's look at one of the carburetors from our engines here at LSU. This is off of a Briggs 950 series. The specific model number is the 130G00. Pretty typical carburetor. Obviously, we have the bowl. We start at the bottom and we move up. This is, I would call, a settling bowl. This is associated with the fuel shutoff lever. We can actually turn the fuel off if we want to run this carburetor out of fuel after we're finished mowing or running our generator or what have you, instead of having to drain the entire tank. You're looking at the choke side here, our choke lever, and that's the choke plate that you can see moving in there. Some people will call that a butterfly, but we're going to call it the choke plate right now. You should be able to see right here, brass here and here, those are two of our jets that we'll get to in a minute. The fuel line is coming towards you, and you can see the hose clamps. We go on this side, we'll see a similar butterfly. This is actually the throttle side, so that's a throttle plate. This particular engine doesn't have a throttle cable that we would manipulate manually, such as maybe some of our walk-behind lawnmowers. This is going to have a throttle spring, kind of more tight with our governor to keep engine running at a constant RPM, and more of like generator type of a capacity. And we see the back end of one of the jets here. All right, so as we take this carburetor apart, I've got my 10mm combination wrench. Most of the bolts on these engines are 10 or 8mm. One thing I'll stop though real quick, you can tell on this carburetor that this is simply the bowl nut because it is silver. Sometimes, and you'll find these are brass, and if you're one of my LSU students, if you're familiar with the small engine CDE, our 900 series have a brass screw right here, and this brass screw as a bowl nut is actually the main jet, again, if that is brass. As we open up the bowl, you'll see there's some residue in there. That's the remnants of gas, and most likely that's the remnants of ethanol, which we'll talk about ethanol fuel a little more detail, and it's probably not necessarily a good idea to utilize ethanol fuel if you're going to store these engines for a long period of time. I usually end up with a gallon of ethanol gas just because it tends to be cheaper, and we don't run these engines enough to actually cause much damage. Next, we'll see kind of more of the inside of this carburetor. We can see this white plastic piece here. This is going to be our float. This is going to work very similar to the float in the back of your toilet, actually. As this moves down like this, the fuel level is low, and the fuel then would, as I push up, would be raised, and it would actually shut off the flow of fuel. And that flow of fuel is going to come from a port right here. I'll remove that pin, lift this up, and you'll see this very small spring on the needle valve. And I'll hold this a little closer to the camera. you can see the needle valve here in this spring. So this is going to be what actually, this rubber tip here is going to be what actually is going to get inserted up into a little port that's going to regulate the flow of fuel. On some of the carburetors, especially older models, that tip's going to be brass, and you start having engine issues as far as flooding especially. It's a good idea to pull this needle valve and check it out to make sure it's a nice sharp point, because sometimes our brass needle valves can wear, or maybe you took the carburetor apart and you dropped and you didn't realize that you bent the tip down a little bit. The rubber ones tend to be either good or not, or functional or not. As we continue to look, now we can actually see the main jet of this carburetor, that brass piece right here. And with a specialized screwdriver, we can actually remove that main jet if we want to take it apart and clean it, which is periodically a pretty good idea. And we have another jet here. And so I've said the word jet several times, and we can also think of these as ports, and this is going to be where airflow is regulated. So in a few minutes, you'll see a video that's going to do a pretty good job explaining how these carburetors work, but in general, I will go over it very briefly. So with our choke off, this is what it would look like. This choke plate is essentially not doing anything right here as far as airflow restriction. And if we back up and we talk about what a choke is what we typically use in a small engine to aid in cold starting. Because as we talked about with the fuel systems, the entire purpose of this carburetor is to vaporize the liquid gasoline and mix it with the air coming through to the combustion chamber. When the fuel is cold, like literally cold ambient temperatures, or even if the engine is relatively cold, starting the engine can be very tough. So if we engage the choke, now you can see that this choke plate is restricting airflow through the main barrel of this carburetor. So what has to happen, the air then, to remember what's going on during when we pull that starter rope, we were starting to engage the 4 cycles of the engine. That piston is going to move down the bore and it's going to create that vacuum. And so now we have made these ports the only area for air, called the high-speed port or high-speed jets, for air to go through the carburetor, and it's going to move faster, and therefore it's going to vaporize fuel more efficiently. Now, what happens once the engine starts here is you can choke the engine out, or you'll start it for fuel. We use the choke to get it started, but once we get the engine started, we typically then have to disengage the choke. A lot of times you also have carburetors have like a half choke, and so you can kind of regulate how much air you want to slowly start letting in, and once the engine warms up, it can run until it runs itself out of fuel. But as we try to look into this carburetor, and I'll try to hold it here, and bear with me while I'm going to adjust the camera just a little bit to let you see maybe a little bit better detail of what's going on here. So now we look in this barrel of this carburetor, you can see the diameter appears to decrease once we get right in the middle of that carburetor, and it's not necessarily that it does appear to decrease, it does decrease, and we can see that piece of brass right there sticking up. That's the other end of the main jet I referenced earlier. So that's where most of the fuel is going to be pushed or pulled up into the carburetor for vaporization. And that narrowing of diameter is called the venturi. And so what the venturi does is just like how an airplane flies. Basically, we're working on what's known as Bernoulli's principle. And so if we look at an airplane wing, so an airplane wing cross section is actually shaped like this. And as the plane is flying this way, air is going to be hit here. And so we have the choices. The air's got to go this way or this way, because its goal is right here. Now, as we can obviously see, the shortest distance between 2 points is a straight line. And so even though we're going from here to here, the air would actually have to travel a little further to get here. Now, air pressure is all about equilibrium. And so for this air that hits right here at this moment, to get here is actually going to have to travel much faster to get here. And so what that's going to do is create what we call lift or differences in pressure. We're actually going to have a pressure difference situation here. And so what happens when this air is moving like this pencil through this carburetor, it's going to hit that venturi and it's going to speed up. Another example to think about this is if you've ever played with an old garden hose, you didn't have a nozzle on it. If you needed to spray your brother or sister, or you needed to get water a little further out, you put your thumb over that hose, and it increases the pressure, increases the speed of the water coming out, and then obviously the distance that you can spray it, because that water is trying to come out of that hose at the same rate, but now you've covered it up. So it hits that, and it's going to go a little bit faster. So if I do a drawing of that venturi, and we know this is the big diameter of the carburetor. We've got that main jet sticking up. We've got a level of gasoline in our bowl. Atmospheric air is naturally just pushing down on this. We have air pressure pushing on us all the time, so does gasoline. And as this air goes very fast through here, it's going to actually hit this main jet, and it's going to pull droplets up into the carburetor, and that's going to then allow that vaporized fuel to come out of this end, and we can control how much air-fuel mix is coming into our engine with our throttle, and so we can throttle down to idle, and we can open it all the way up. So throttle down, wide open is exactly where the saying comes from. And from there, the gas fuel mix will enter the combustion chamber, and hopefully the spark will ignite it. To help clarify Bernoulli's principle that I mentioned in the last video, I have another short video following this slide that's going to demonstrate Bernoulli's principle for us. So we just discussed the basics of carburetors and how they work. And one of the concepts I mentioned was Bernoulli's principle. And so I want to do a quick demonstration to basically show you what's going on inside the venturi of a carburetor. So in front of me, I have a cup of just tap water, straw, and a napkin to catch the water vapor. I'm going to use a second straw to get the water out of the cup. Adjust the camera real quick so you can see what I'm doing. So I'm simply going to blow air straight across the straw that is into the water, and that increase in velocity of the air moving over the straw will actually create an area of low pressure right at the top. And when we have areas of low pressure, nature basically just seeks equilibrium, and so water is going to be pulled up the straw and should, hopefully, if this goes well, be captured onto this paper towel. So let's give it a go. All right. Not sure if you can see the vapor coming out or not, but the paper towel is most definitely wet. So we definitely utilize Bernoulli's principle to remove the water from the cup using only air pressure. So again, the increase in velocity as the air was moving faster over the straw created low pressure, and it was able to pull this water up the tube, which would have, I guess we could say, was representing our main jet in a carburetor. So now that we've had a basic discussion of carburetors, following this slide, I have a short, 15-minute or so video from Briggs & Stratton that does an excellent job discussing carburetors in a little bit more detail.
One of the most misunderstood and, as a result, incorrectly diagnosed components of any internal combustion engine is the carburetor. In the next few minutes, we'd like to discuss the theory and function of the carburetors used on Briggs & Stratton engines. Now, there are a couple of ways we could go about this. First, we could discuss every type of carburetor used on every Briggs & Stratton engine. Look at all the detailed passages discuss where they go, how they work, what they do, and then try to cover every problem that may be associated with each carburetor. Problem with that approach is it would take hours, and by the time we got to the last carburetor, you probably wouldn't remember anything we said about the first one. I think a better approach is to build a generic carburetor model based upon carburetor theory, and along the way explain the function of each of the systems we build into our carburetors. The first step to understanding basic carburetor theory is to define just what a carburetor is. Webster defines a carburetor as an apparatus for supplying an internal combustion engine with atomized and vaporized fuel mixed with air in an explosive mixture. This definition could fit a number of different things. For example, a very simple carburetor could consist of nothing more than a gas tank with a fuel shutoff valve leading into a hollow tube attached to an engine. The biggest problem with this setup is that you'd have to constantly adjust the fuel flow with the shutoff valve in order to keep the engine running at a given speed under varying engine loads. Now, even though this apparatus would function as a carburetor, I think you can see that it's impossible to expect anyone to actually use one on an internal combustion engine. Instead, let's build a carburation system that's more self-sufficient, that's capable of adjusting for changes in engine speed or load. To do this, we'll start with a simple tube. One end of the tube should have a flange that allows us to attach the tube to the engine. This is the beginning of our carburetor. The tube is used to direct the airflow into the intake port each time the piston moves down the cylinder with the intake valve open. Keep in mind that as the piston moves down in the cylinder, a void or vacuum is created in the cylinder, and the air surrounding the engine is pulled into the cylinder in an attempt to fill the void. That is, providing all things affecting engine compression are functioning properly, such as valves, gaskets, and rings. That takes care of getting air into the combustion chamber, but how does the carburetor get the atomized or vaporized fuel into the combustion chamber? First, we need a fuel supply. We take care of that by adding a bowl of fuel below the tube. But that creates another problem. How do we get the gasoline from the bowl below the tube into the air passing through the tube? Now here, we have to refer to Bernoulli's principle of fluid flow. We can treat air as if it were a fluid and apply part of Bernoulli's principle to our carburetor in order to get the fuel out of the bowl and into the airstream. In part, Bernoulli's principle states that if you increase the velocity of a fluid within a confined area, the pressure of that fluid is decreased. Now, if we apply that concept to our carburetor, increasing the velocity of the airflow in the tube will decrease the pressure of that air. To increase the velocity of the air, we'll use a narrowing in the tube, commonly called a venturi. Now, as air passes through the tube at a constant speed, the only way for it to pass through the venturi is to increase in speed. Speed with direction is velocity. As the air velocity increases through the venturi, the pressure decreases, and we end up with a low pressure area within the carburetor's venturi. This principle is actually a common day-to-day occurrence. Most of you have probably flown in an airplane at one time or another. Well, if you take a look at a sectional view of a venturi, you'll notice that it is shaped very much like an airplane wing, and in fact, it works very similarly. As the wing passes through the air traveling over the wing has to travel farther, and as a result, faster than the air below the wing. This creates an area of lower pressure on top of the wing and higher pressure below the wing, which generates lift and allows the airplane to fly. By the way, the same principle is used by baseball pitchers to throw a curveball, but drastically increasing the curve involves changing the outside surface of the ball. It's where sandpaper or Vaseline comes into play. Anyway, let's get back to our carburetor. Now that we've created some pressure differences, we can use them to do work, or, in our case, to push fuel. We'll start by connecting our fuel supply to the venturi with a small tube. Taking into account that air pressure at sea level is 14.7 psi, when air flows through the venturi, it creates an area of pressure that is lower than 14.7 psi. Areas of higher pressure always move toward areas of lower pressure. In this case, if we happen to put some gasoline between the high and low pressure areas, the high pressure will try to move the gasoline out of its way in order to reach the lower pressure, thus pushing the gasoline up through the tube and into the airstream, moving through the carburetor and into the engine. We still have one problem with our model carburetor, and that is that we need to get sustained high pressure on the fuel in the bowl of the carburetor. We can easily do this by adding an atmospheric vent, more commonly known as a bowl vent. This allows the air pressure to continually press down on the fuel in the bowl, pushing it up the tube into the carburetor, where it will be mixed with the air moving through the tube into the engine. What we end up with is a simple carburation system for our engine. Unfortunately, this carburetor allows the engine to run at one speed and one speed only, with no control over the amount of fuel that the engine is receiving. We can control the engine speed by adding a throttle plate to control the airflow. When the throttle plate is fully opened, it allows the maximum airflow, which increases the difference in pressure between the surrounding air and the air moving through the venturi. As we close the throttle plate part way, it decreases the flow of air, which also decreases the difference in air pressure, and as a result, decreases the amount of fuel flow. One thing we have to keep in mind, though, is that there are all sorts of factors that affect an engine's performance. We'll need to add something to our carburetor to give us better control of the fuel flow through the pickup tube and into the airstream. We can either add an adjustable needle to the pickup tube, or we could put in a fixed jet that meters a specific amount of fuel calibrated to the engine's needs. That takes care of most of the high-speed problems, but we still haven't perfected a way to run the engine at a very slow speed. We can keep closing the throttle plate to slow the engine. Eventually, we'll reach the point where we've reduced the airflow so much that there is no longer a sufficient difference in pressure between the air in the venturi and the outside air to push the fuel up the pickup tube. In order to solve that problem, we'll have to add an idle system to our model carburetor. As the throttle plate closes and we lose the pressure difference between the venturi and the atmospheric pressure on the gasoline in the bowl, we gain some significant pressure differences in some other areas of the carburetor. One place where we gain a significant difference in pressure is between the engine side and the venturi side of the throttle plate. As the throttle plate begins to close, the air moving past the throttle plate increases in velocity, trying to get into the engine in an attempt to fill the void created as the piston moves down the cylinder bore. Remember Bernoulli's principle. With that increase in velocity comes a decrease in pressure. We'll use that pressure difference to operate our idle system. If we create a passage from the fuel in the carburetor's bowl to the engine side of the throttle plate, close to where the throttle plate would contact the inside of the tube, we can use the area of low pressure around the throttle plate to allow the higher outside atmospheric pressure to push the fuel through the idle passage and into the airstream going into the engine. Now, when the throttle plate is open, the fuel is pushed up the high-speed pickup tube. As the throttle plate begins to close, the fuel drops down the high-speed pickup tube and fuel is pushed up the idle fuel passage into the airstream. Like the high-speed system, it's to our advantage to be able to adjust or fine-tune the amount of fuel entering through the idle circuit. Once again, we'll add an adjustment needle to the idle passage, which restricts fuel flow and allows us to meter a precise amount of gasoline that is calibrated to the engine's needs. Now that we've installed the idle fuel adjustment needle, we have completed our basic carburetor. If we attached it to an engine, it would do the job. However, we can still make a few improvements, like one that will make the engine easier to start when it is cold. For this, we'll add either a choke or primer system. First, with a choking system, we can install a choke plate. When the choke plate is closed, it simply blocks or restricts airflow through the carburetor. Keep in mind that every time the piston moves down in the cylinder bore, It creates a vacuum that the high pressure surrounding the engine will try to fill. By restricting the flow of air at the front of the carburetor, a low pressure area is created throughout the carburetor behind the choke plate. The higher atmospheric pressure then pushes fuel into the airstream from the high-speed system, which creates a very rich fuel mixture for cold starting. If you were to use a priming system instead, the atmospheric vent is blocked off when the primer bulb is pushed. This increases air pressure in the bowl of the carburetor, forcing fuel from the high-speed system into the airstream. This is usually referred to as a dry bulb priming system. Now that we've taken care of the cold starting problem, let's discuss another improvement we can make to our carburetor. You see, contrary to popular belief, gasoline does not burn. Gasoline vapors burn. And the more we can vaporize or atomize the fuel before it enters the combustion chamber, the better and cleaner the engine will run. To do this, we can start by premixing the fuel with air. We'll do that by adding an air bleed to the high-speed pickup tube of our carburetor. Now, when the pressure differences are created between the venturi and the air pressure in the bowl of the carburetor, not only will fuel be pushed up the high-speed pickup tube, but a metered amount of air will be entering the pickup tube at the same time. This starts to break up and atomize or vaporize the fuel before it even enters the carburetor's venturi, as well as offering low-pressure relief under no-load conditions. The same thing can be added to our idle system. By adding an air bleed or a metered diameter hole to the idle system, premixing of the fuel and air will take place before it enters the airstream going into the engine. The air bleed also prevents extremely rich running at no-load idle speeds. By adding these two air bleeds, we have increased the efficiency of the engine, as well as provided for much better fuel efficiency in the carburetor. There is one last modification we can make to the carburetor that has to do with improving the smooth acceleration of the engine from an idle RPM to a top no-load governed speed. When we switch from the idle circuit to the high-speed circuit, there is a momentary lapse or lull in fuel transfer from the carburetor's bowl to the airstream entering the engine. We can improve the engine's acceleration by adding some transitional fuel passages to the idle system. Now, as the throttle plate opens and the engine accelerates, fuel is added to the airstream from the transitional passages to maintain the fuel supply to the engine when going from idle to high speed. With that, we have completed our basic carburetor. The only problem we have left is that once the carburetor bowl is empty, the engine will stop running. Fortunately, that can easily be remedied by adding a system that maintains a constant fuel supply to the bowl of the carburetor so that the engine can run as long as the fuel supply lasts. We start by adding a float to the bowl of the carburetor. The float is connected to a needle. As the float moves up and down according to the fuel level in the bowl, the needle opens and closes to either allow more fuel in to bring it back to its proper level or shut off the fuel supply completely. With that, we have a working carburetor that can sustain engine operation as long as the fuel supply lasts. Now comes the important question. How does all of this apply to Briggs & Stratton carburetors? You see, it's really quite simple. Every one of Briggs & Stratton's carburetors function using one or more of the principles we've just discussed. It doesn't matter whether you're talking about a downdraft carburetor, an updraft carburetor, or a side draft carburetor. It makes no difference whether it's a Pulsajet, a VacuJet, a one-piece flow jet, or a two-piece flow jet carburetor. They all function using some of the exact principles we've just discussed. At Briggs & Stratton, we know that your business depends on your ability to quickly diagnose and repair engine problems. By remembering how we built this basic carburetor, you should be able to understand most of the carburetor problems that come your way.
All right, now that we've gone through a little bit of carburetor theory, how carburetors work, the purposes of carburetors, I think it's a good place to talk about troubleshooting carburetors because as the video said, carburetor problems are relatively common. In fact, I was at a training several years ago with Briggs and Stratton, and that technician trainer estimated 80+% of the issues technicians see are usually carburetor related. And that usually ends up being something like dirt or debris in the carburetor, or commonly has to do with ethanol fuel. Now, I want to take a moment and talk about ethanol fuel. Ethanol is a fine source of energy in engines that are rated for ethanol. Um, Most small gasoline engines are not ethanol compatible. Now, I know some of you may be thinking, well, I use ethanol mixed gas in my lawnmower all the time, and to be quite honest, so do I. It mostly because it's a lot more convenient for where I live to go to a gas station that has an ethanol blend versus driving several miles out of my way to find a station without ethanol. The problem tends to come when ethanol sits in tanks. Ethanol, as an ethanol alcohol, is a very good solvent, and what solvent means is that it's good at dissolving things. And that is an unfortunate situation when we're in a small engine world, when the things it's dissolving tend to be rubber gaskets or some of the seals in our engine, and then we get this gunky, sticky residue that can start to build over time. So every small engine manufacturer will tell you just don't use ethanol fuel in your engine. If you're going to anyway, the best thing I can tell you to do is to run your carburetor out of fuel every time you use it. If you have a shutoff on your carburetor, like the one we looked at earlier, that's easy. You can turn the fuel off to the carburetor and run it out. That, or try to only put enough gas in to get your yard motor or whatever. This is probably more important during long-term winter storage. If you're mowing your yard every week or every few days, you probably won't have an issue, but still, these engines are not rated for ethanol fuel. So before we just jump right into taking a carburetor apart because our engine won't start, it's good practice to check a few easy things. More than once, I've helped somebody with an engine that wouldn't start, and it simply didn't have any gas. It just didn't have fuel. So ensure that the fuel is in there, that it's fresh and clean, and the tank's not all rusty. So just pop the top off of your gas tank and look in it is an easy way to do that. And just see if there's fuel in it. If it just looks rusty, you might need a flashlight to look kind of down in there. Gasoline will degrade after a period of time. You can also maybe check fuel lines. They can become blocked. I can remember, this isn't a small engine story, but years ago, when I was probably middle or high school, we had an old tractor. It's a 1953 Ford Jubilee tractor, and I used to rake hay with that tractor with an old 5-bar side delivery New Holland rake. And one day, we were getting ready to start for the day, and I could not get that tractor to start. Now, she was old even then, but would always start. And we worked and we've tried to figure things out. And after not taking the advice I'm giving you now, start tearing carburetors apart and everything else, we pulled the fuel lines, and somehow or another a June bug had gotten into the gas tank. Maybe it was in the gas can, who knows? But it got in there and ended up getting in partially into the fuel line and blocked it. So you just never know. After that, got that beetle out of there, and she started right up. Check your fuel filter. If your fuel filter is overly dirty, or if it's also got a water separator, you can see if you have water in your fuel. Always check that. You can prevent fuel flow with a dirty filter, or restrict flow to where it won't run properly. And one that is really easy for anybody to check that is almost always ignored is your air filter. So the air filter is going to be what prevents a lot of the junk from getting into your combustion chamber or your engine. And that thing can get so plugged up that it can't allow air to enter the carburetor and atomize fuel. So if we can check the fuel tank, fuel lines, fuel filter, sometimes we can find that we have a really easy problem to correct, and then we can go about our work. So if we've checked those few easy so to speak, things, and we still can't figure it out, then it might be time to maybe take our carburetor off, maybe clean it, tear into things a little bit further. But we need to think about what's going on. And so we have two really broad symptom types. We either have an engine that won't start or an engine that runs poorly. And it's hard to tell which one is worse or more frustrating. An engine that simply won't start, or one that you can get to run, but will do something like die as soon as you try to put it under load, which means like mow your grass, split the wood if it's a log splitter, engage the pressure washer, or turn on your generator. That can be pretty frustrating because then you almost always immediately restart it and it'll idle, but it won't run under load. Many of times, again, it's dirt and debris in the carburetor, and we can fix that sometimes by simply taking the bowl off and cleaning it out. Sometimes it's going to take a little bit more effort, and we're going to have to actually clean the jets out. That's could entail utilizing carburetor cleaner. That could utilize parts cleaner, and we have to soak it for 24, 48 hours. And sometimes it's also a point where whatever piece of debris in there, it might be a time to either take it to a technician to see if they can get whatever is in your jets out, or sometimes the technicians will even tell you, yeah, I can fix this, but it's going to be cheaper for you to just simply replace your carburetor. A pretty standard Briggs carburetor is going to run somewhere between $30 and $50. The time it would take a technician to disassemble and clean the jets would probably, hourly rate would run more than that. To discuss a little bit more about carburetor diagnostics and troubleshooting, after this slide, there's another Briggs & Stratton video that does an excellent job of discussing carburetor diagnostics. I've also got a PDF, kind of like a decision tree on Moodle, and that I'll also share with other folks that may be utilizing this video across Louisiana. I know some of our other universities might be utilizing this, so I will get that PDF of carburation diagnostics out to Dr. Smith for distribution to everybody.
Do you remember the first time you diagnosed a carburation-related problem? It might have been last year or 20 years ago. Whenever it was probably frustrating and resulted in a lot of wasted time. Briggs & Stratton recognizes that many new technicians struggle with understanding the variety of carburetors they're exposed to on a daily basis. Even seasoned technicians still struggle with carburation-related concerns. Many technicians have diagnostic tools in their arsenal. Using those tools effectively can reduce the equipment service time. However, those aren't the only things you need for diagnostic work. You also need experience, a clear understanding of what the symptoms of the problem are, and knowledge about what causes them. During this update, we're going to list the common symptoms that cause warranty and service-related issues for carburetors. Then we'll investigate the many causes of those symptoms. To help us better understand carburetors, let's review the 4 cycles of a properly running engine and carburetor.
4 elements are required in an internal combustion engine to allow it to run. Those elements are air, fuel, compression, and spark. Air and fuel enter the engine through the carburetor. It's the job of the carburetor to supply a mixture of air and fuel that will allow proper combustion. During the intake stroke, the intake valve between the carburetor and combustion chamber opens. This allows atmospheric pressure to force the air-fuel mixture into the cylinder bore as the piston moves downward. Just after the piston reaches the bottom of its travel, or bottom dead center, the cylinder bore contains as much air-fuel mixture as possible. The intake valve closes, and the advancing piston returns back up the cylinder bore. This is the compression stroke. The air-fuel mixture is compressed between the piston and cylinder head. When the piston reaches the top of its travel, called top dead center, the air-fuel mixture will be at its optimum ignitability point. A very high voltage is created in the ignition coil. The spark plug enables this high voltage to be discharged into the combustion chamber. The heat created by the spark ignites the gases, creating rapidly expanding superheated gases, forcing the piston down the cylinder bore during the power stroke. When the piston reaches bottom dead center again, the exhaust valve opens. As the piston travels back up the cylinder bore, it forces the spent combustion gases through the exhaust valve and out of the exhaust system. As the piston returns to top dead center, the exhaust valve closes, the intake valve opens, and the 4 cycles repeat.
Now that we've reviewed a properly functioning engine and carburetor, let's list the most common symptoms that can cause carburation, warranty, and servicing issues. A. The engine will not start. B. The engine is hard to start. C. The engine starts but will not idle. D. The engine starts and idles but will not run properly at top no load. E. The engine starts and idles but shows slight hesitation with possible stalling while performing light to moderate work. F. The engine starts and idles but will not run under load. G. The engine starts, idles, runs at top no load and under load, but stops running after a short period of time. H. Engine oil dilution occurs when the engine is not running. And I. Engine oil dilution occurs only when engine is running. Now that we have a list of common carburetor symptoms, let's analyze the cause and effects related to each one. The systematic approach of troubleshooting displays well on a flowchart. Following a well-designed flowchart can make problem-solving nearly effortless. It's similar to using a road map, because each time you come to an intersection, you have to decide where to go next. With a flowchart, you base your decisions on the diagnostic tools, your own experience, or advice from a more experienced technician. From here on in, we'll use our carburetor symptoms to build a detailed carburetor diagnostics flowchart which should make solving future carburetor problems easy. A carburetor is a mechanical device that combines fuel and air. The fuel and air are usually metered and mixed. It stands to reason then that problems will typically be with the mechanical nature of the device and/or with the delivery of fuel and air in the proper proportions. Carburetors use fresh fuel, clean air, and up to 4 moving mechanical parts. The mechanical parts are choke shaft, if equipped, throttle shaft, float, and inlet needle and seat. If any of these are unable to perform their function, the carburetor will fail to perform properly. Following a systematic diagnostic approach is important. It's important to check and verify each step. We've made some presumptions for this program that a thorough quick check has been performed, such as fresh fuel is present, the choke operates as it should, etc. With this in mind, let's get started. In our first example, the symptom is A. The engine will not start. Dirt and debris has been and continues to be the #1 problem for carburetors. We need to better understand what dirt or debris is and where and how it enters the carburation system. Dirt is a natural substance that can find its way into the carburetor through the air intake or dislodged gaskets. Dirt can also enter through the fuel system when the customer removes the gas cap, or directly from a contaminated supply tank. Depending on the type of fuel filter being used and the size of the particles of dirt, the carburetor may never be affected. Now that we understand what dirt is, let's look at debris. Debris is an unnatural substance, such as plastic, rubber, or metal shavings. When material other than fuel is found within a fuel system, making a distinction as to what the material is and where it was found can aid in establishing how it got there. Sometimes the type of material can even establish who is at fault. For instance, small black plastic chips found plugging a fuel inlet on a brand new lawnmower featuring a black plastic fuel tank may place the blame on the manufacturer. Non-professional servicing practices such as dirty repair benches or using bolts to plug fuel lines will cause dirt or debris to enter the system. It's like a surgeon who doesn't wash his hands before an operation. A carburetor repair bench should always be kept clean. Fuel line clamps should be used when disconnecting any fuel lines. Fuel filters can control some of the dirt and debris that enters the fuel system during equipment usage. Briggs & Stratton has always offered a fuel filter with its engines. Ultimately, original equipment manufacturers decide what fuel filter will or will not be used on the application, with the exception of most Briggs & Stratton fuel tanks that come standard with fuel filters. Fuel filters are rated by the size of debris the filter will not allow through the filter median. This measurement is referred to as micron size. There are 25,400 microns in 1 inch. By comparison, an average human hair is 40 to 300 microns thick. If passing debris is smaller than the smallest orifice in the carburetor, it won't cause a problem, unless enough fine particulates pass through the fuel filter and coagulate in the carburetor passageways. Eventually, it could cause an obstruction, similar to an obstructed artery in the human heart. When the fuel filter becomes clogged with dirt, debris, or water, the flow of fuel will stop and not let the fuel through. If dirt or debris in the fuel manages to flow through the filter, it will end up in the carburetor bowl. If the dirt or debris lodges in the main jet, the fuel cannot flow up the high-speed circuit to start the engine. Other symptoms that can occur with a clogged or partially blocked main jet are F. The engine starts and idles but will not run under load. And G. The engine starts, idles, runs at top no-load speed and under load, but stops running after a short period of time. The flow charts for these two symptoms follow very similar paths. If dirt or debris partially blocks the main jet while the engine is running and a load is applied, the carburetor cannot supply enough fuel to keep the engine running. Known also as a loss of power, the engine stops running and the dirt falls away from the main jet, resulting in the customer being able to once again start the engine. The customer can continue performing some work until the dirt once again becomes temporarily lodged in the main jet. This cycle will repeat itself until the dirt becomes permanently lodged in the main jet, causing a permanent no-start symptom. Let's look at symptom C next. The engine starts but will not idle, resulting in a pronounced hunting and surging. This symptom is the result of dirt or debris lodging in the fuel idle circuit. The dirt or debris can be introduced from the fuel tank system or an external bowl vent. Remember, the external bowl vent is typically not filtered since there is very little airflow. If the idle fuel passageway is completely clogged, the engine may try to stall. Then, as the engine begins to coast down, the governor spring opens the throttle plate. This is a normal function for the governor spring. As the governor spring opens the throttle plate, the low pressure area moves above the main nozzle. This causes a shot of fresh fuel to enter the carburetor and engine speed increases. The result is hunting and surging. To override the governor, simply hold the throttle plate closed to force the engine to idle. If the engine continues to run, you know there's a problem with the governor system, and you would need to troubleshoot the governor. If the engine stalls, you need to inspect the fuel supply route to the idle circuit. The smallest fuel orifice in most float feed style carburetors is the idle circuit pilot jet. These carburetors can have an idle air orifice size as small as 24 thousandths of an inch, and an idle fuel pilot jet orifice as large as 2 1/2 thousandths of an inch. An otoscope is a great diagnostic tool to help see those small orifices and reinforce your learning experience. Dirt and debris entering through a ripped or torn air cleaner can collect in the idle air circuit, causing it to become clogged before the pilot jet. When this occurs, the pilot jet will only flow raw fuel to the combustion chamber at idle, resulting in light black smoke exiting the exhaust. The carburetor will mildly hunt and surge due to this symptom. If the carburetor has an idle mixture screw, you can use it as a diagnostic tool. While the engine is running, adjust the idle mixture screw until the engine runs smoothly. Shut off the engine, and while turning the idle mixture screw in until it bottoms out, count the number of turns. If the idle mixture screw was less than 1 turn out, There's a good chance the idle air circuit is clogged. Now let's go back to symptom B. The engine is hard to start. A choke-style carburetor exhibits harder starting when the high-speed air circuit is clogged. The high-speed air bleed acts as a vent to allow the fuel to be drawn up the emulsion tube. When dirt or debris enters the high-speed air circuit, it stops the airflow from reaching the emulsion tube. The carburetor cannot mix the air and fuel when the engine is trying to start or when the engine is under a heavy workload. The visual sign of a clogged high-speed air circuit under load will be black smoke from the exhaust and the possible loss of power. Most carburetors require the ability to handle light to moderate workloads. If those passages become partially or totally clogged, the carburetor's symptoms can be similar. Let's take a moment to identify those carburetor symptoms and then follow the diagnostic flowchart. D. The engine starts and idles but will not run properly at top no-load speed. E. The engine starts and idles but shows slight hesitation with possible stalling when light loads are applied. Dirt and debris can enter the transition ports 3 different ways, resulting in similar symptoms. The first path is when dirt or debris enters the idle air bleed and mixes with the fuel in the pilot jet. The dirt or debris continues to the transition ports behind the small round Welch plug. When the transition ports become partially or fully blocked, the engine will hesitate when the engine is under a light to moderate load. The second path is when dirt or debris enters from the fuel system, such as the fuel tank, and then into the carburetor bowl. The final entryway can be the carburetor bowl's vent. The bowl vent does not experience a high volume of moving air. However, the bowl vent is exposed to the environment around the carburetor, so dirt and debris could enter the carburetor bowl. The 2 last symptoms that occur are engine oil dilution occurs when engine is not running, and engine oil dilution occurs when engine is running. These symptoms, H and I, can be the easiest to identify and fix. In some cases, you need to educate the customer on how to use the equipment. Many of you have had a customer tell you they had a gusher when checking the oil. When they removed the oil fill cap, oil poured up and out of the hole, as if the engine had mysteriously increased its oil volume. Of course, no engine adds its own oil, even though that's what some customers may describe. The symptom of oil dilution when the engine is not running is typically caused by dirt or debris becoming wedged between the carburetor's needle and seat. It can also be caused by the float hinge pin sticking, or a defective or misadjusted float. When this occurs, it allows the fuel to continually flow through the carburetor intake manifold, through the intake valve, down the cylinder wall, and into the crankcase. This condition is called cylinder wall wash and will eventually cause a failure of the piston rings and cylinder wall. One additional condition that can occur while the engine is not running is float bounce. This occurs when the equipment is transported on a trailer or in the back of a car or truck. If the fuel supply shutoff valve is not turned off, the float can bounce. When the float bounces, it opens the needle and seat, allowing unwanted fuel into the carburetor bowl. When enough fuel overfills the bowl, the excess fuel migrates to the crankcase. A quick and easy fix is to install a Briggs & Stratton fuel shutoff valve in line between the fuel tank and carburetor inlet. The final symptom we're going to look at is when the engine oil dilution occurs only when the engine is running. If at any time the carburetor is not adjusted correctly, causing a rich running condition, the extra fuel will not all be burned. This results in oil dilution, and in some cases, when an engine is cold and not allowed to properly warm up before it's shut down, unburned fuel vapors will gather and condense in the crankcase. We've even seen twin-cylinder engines that have been run for months, if not years, on one cylinder, resulting in oil dilution failures. A bouncing float can also occur with a running engine. If the equipment is running over rough terrain, the float will bounce. Some fuel inlet needles are designed to compensate for this situation. The needles have small springs on the back where they make contact with the float. These small springs act like small shock absorbers. Diagnosing and repairing carburation-related problems requires more than having the right tools. It's a clear understanding of what the symptoms are and what is supposed to happen when the equipment runs properly. Use a systematic approach of working through the symptom, and you will be successful every time.